from Columbia University and Princeton University, the index and the vertex.
Thanks, John. Well,
Next.
Right. So it's great to be here, and this talk will be what I'm going to explain just completely elementary. There are some non-elementary aspects to this, but they won't be explained. I'll leave it to Nikita if you have any questions. So first is just to make sure we're all on the same page. I'll read for you, or we'll see on the projector some pages from textbooks, and the textbooks, the concerns will start with just quantum mechanics. Okay, this is why we. This says if I have a motion of a quantum particle in a manifold in a potential, then I have to look. Then the evolution operator is exponential of minus IT h, where h is the Laplace operator in that potential. Okay, so far so good. And in particular, we'll be interested in a situation when time, first it's Euclidean, and second it's a circle of length L. So my partition function now trace exponential of minus L times the Hamiltonian. And the trace is taking over L2 of x. So if h was a non-negative definite operator, this converges nicely, defines. Well, okay. Nothing happened so far. Now,
What is L?
length of the circle.
Oh.
Time. There was a. See, there was evolution was taken to some time t. Now that time is first Euclidean, so you remove I, and second you set it to be L. So now if there are fermions in the theory, then you can in principle consider periodic or anti-periodic boundary condition. We'll take periodic, and so in which case, this is the partition function. You have to take. Yeah, right. That's right. So that in this case, this trace you should take the trace in the presence of fermions. Your Hilbert space is Z2 graded. There's even vectors and odd vectors, and you have to take trace over the even and subtract the trace over the odd. Okay. You might as well be finishing lunch right now. So it's nothing happening. So and now what's in supersymmetric situation, this is characterized by the fact that H is an anti-commutator of some operator Q with its adjoint. And the Q has to square to 0. An elementary algebraic consequence of this relation, okay, is this: if I look at the eigenvalues of H, then those which are non-zero, Q will pair. For every even eigenvalue, it would be an odd eigenvalue of the exact same magnitude. So Q will just pair them. And for zero eigenvalues, it may kill some, it may pair some. And so in particular, if I now want to compute the super trace of exponential minus h, well, this is the sum over all energy levels. But you see this is whatever contributes with the plus exactly contributes with the minus, so it cancels out. And we left only the computation on the zero energy level. So first the super trace is just the super dimension of the kernel. Kernel is what's the blue dots here. And then moreover, Q pairs some of these dots to these dots. So you might as well take the super dimension of the kernel of Q divided by the image of Q. Since Q squares to 0, image is in the kernel, you take this quotient. And so this quantity is called the cohomology of Q, and its superdimension is called the Euler characteristic. And in particular, very elementary consequence of this is that this is independent of L. Just completely topological. Right? What? Oh yeah, sure, yeah. Thanks. So this is so an example of this is what's called Landau-Gisbert quantum mechanics. Is when you start with with a Kähler manifold X, then your Hilbert space, which will be the space of differential forms on this. Okay, look, this is you're gonna. So this should be X. I apologize. So you look differential forms on X. This is Z2 graded by the degree of the differential forms, and my operator Q, which the Hamiltonian will be the QQ star plus Q star Q, is this operator. It's the d bar differential plus exterior product by the differential of a holomorphic function. And since W is holomorphic, this squares to 0, and that's squares to 0. If I compute QQ the Hamiltonian, then from the QQ star part, I'm going to get a potential, which is the norm square of this section. So that's an example. That's basically an example to have in mind, to keep in mind. And if we're interested in the partition function of this, then we can know that this is Q squares to 0, but moreover, the d bar individually squares to 0, and wedging by differential of a function individually squares to 0, and they anti-commute. So if we want to compute the Euler characteristic of a complex where this is the differential, we might as well first take the cohomology, the d bar cohomology, and then take this cohomology. And if we take the d bar cohomology, then we're left with the d bar has only kernel, no cokernel, and so that you'll be only looking at differential on holomorphic forms on X. And on holomorphic forms on X, we have a complex which is the exterior wedging by okay. So the Euler characteristic of this complex is the partition function of Landau-Ginzburg. And this complex is obviously somehow visibly exact away from the if this is non-zero, then this complex is exact. There's no cohomology. And if there is a zero of the derivative, that is to say, if there is a critical point, then there is some cohomology, and the critical point is not degenerate, that it happens in this dimension, and it degrees 1. And so if all critical points are degenerate, then the partition function is this. And some critical points are degenerate, then they make its own contribution. But that's roughly. Okay. Yes. All right. So now, if we're interested in quantum field theory in d plus 1 dimension, this formally completely similar. It's in the sense that instead of our finite dimensional manifold, you have to take the manifold of all possible configuration of fields in d dimensions. Something very, very big. But formula is the same. However, miraculously, maybe I don't know. This is the kind of phenomenon on this sort of. This is extremely well known, and that's exactly the kind of phenomenon why it's interesting to have the center. But it's still a miracle that very often the cohomology of this huge infinite dimensional complexes reduces to something just the complex of the finite dimensional vector bundles over finite dimensional manifolds. Or maybe more important provides us usually a countable union of such. And that is a countable union that makes things interesting, because you still have.
You're not saying the cohomology reduces, you're saying the complex is equivalent to this small.
Well, in particular, it's a reduced decomposition. But in fact, the actual an actual complex quasi-isomorphic with something just finite dimensional. Right. But then having it maybe I'll make a philosophical comment. Make it a countable union. Here's what it makes interesting, because otherwise, this is why things still in some sense infinite dimensional. Why you can still have series that have singularities, etc., etc. Why is it interesting to study those? We'll just find Lemon and I'll do that. But and for a well-known example, we're going to take this n equals 2 supersymmetric gauge theory in 4 plus 1 dimensions. in which case this stuff reduces to cohomology of some vector bundles over the moduli space of instantons in 4 dimensions. So you start with configurations of all gauge fields in 4 dimensions, and that's this is some kind of very big space. But you end up with just instantons, which are fine dimensional things for given topological charge. And there is, and as I said, it's interesting, but the topological charge could be any integer, and so I have an infinite sum, and that infinite sum gives you an interesting function. Otherwise the partition function would be just a polynomial, not so interesting. And Nikita, who's here, who was standing on the shoulders of giants who are also here, and so look, it's not the place to review this, but it's good somehow. This been completely worked out, and the key ingredient here is this moduli space of instantons. Well, you can either define them as non-singular algebraic varieties, or you can define them as singular, and then there's a nice desingularization. And so it's essentially what this reduces to is computing cohomology of vector bundles over smooth algebraic varieties. And this is why the theory is so nice. Okay. And our goal is to do something like this in 6 + 1 dimensions. And the reason I'll explain in a second why we're interested in this, and what are the difficulties, but the basic difficulty is that the moduli of 6-dimensional instanton is nowhere near as nice as 4-dimensional ones. And then one has to have a certain ideas, well, maybe not as profound as some other ideals mentioned so far, but still maybe slightly non-trivial ideas how to proceed. And the motivation for studying this comes from 2 ways to write this equation. And so, okay, this is. Okay, very well. Yeah. Yeah, right. Yeah. Yeah. So it's n theoretic consideration that say that there's certain correspondence between 4 gauge theories in 4 + 1 dimensions and 6 + 1 dimensions, and the kind of correspondence goes like this. So one takes 11-dimensional manifolds of the kind which is a 4-dimensional Calabi-Yau, and 6-dimensional. These are real dimensions. So I mean it's a complex 2 and a complex 3 and a circle. And so and then we can view this theory from the perspective of 6 + 1 or 4 + 1 dimensions. And in both cases, if the volumes of both x and y's are infinite, we should get a gauge theory in 4 + 1 or 6 + 1 dimensions. Okay, well, I don't know what I mean. Certainly, I don't know. Maybe some other people know. I don't know what's the theory on the whole 11-dimensional manifold. But certainly, what the theory which is in 4 + 1 or 6 + 1 dimension. This is something we can at least in 6 + 1 dimension we can suggest what it is. Or in 4 + 1 dimension is the ordinary gauge theory. And this setup, there's been a notion very popular in recent times. This setup one can refine in the sense that one can have an isometry of both 4-dimensional and 6-dimensional manifold that rotates so this rotates the Calabi-Yau form here by a certain phase, and this rotates the Calabi-Yau form by the opposite phase, so that the total, the product of two forms here is invariant. And so then you can use this isometry to, instead of forming a direct product with a circle, you can inform. So what refinement is about is just a test of our understanding of the theory. So if I have an isometry of x and y, I can twist them as I go around the circle. If I make a turn around the circle, instead of gluing, instead of gluing the beginning to the end, I simultaneously rotate x and y, and I rotate them in the opposite direction, meaning by the phase of the 3 form, so that the whole thing it has a invariant holomorphic phi form. And this, right? So that this means in the whole setup, if I have such an isometries, I should pick an extra parameter for this. All right. So from constructions, clearly the case should be the case that if the partition function of the entire M theory on this product, I can view it as a partition function of a certain gauge theory depending on X. That is a gauge theory that means gauge theory depending on X on the manifold Y cross S1, or gauge theory depending on Y on the manifold X cross S1. And this should be equality. And then you're right, but the theories, this 4-dimensional and the 6-dimensional theories are very different, or not very different. And in 4 dimensions, we have the very familiar supersymmetric gauge theory, with the partition function being just the Nikita's partition function. And this has parameters, has some discrete and continuous parameters, and those are set by. So this is a gauge theory depending on X. First, it has some gauge groups, matter fields, discrete parameters, and these are set by the topology of X, and it has some coupling constants, some continuous parameters, and those are set by the geometry of X. And what I mean is, in more precise terms, is that the gauge bosons and the matter fields in 4 dimensions, they come from certain holomorphic spheres in the Calabi-Yau X, and so this is somehow the content of this is determined by the topology of X, and the coupling constants are determined by how big the spheres are, by the actual metric on X, by the actual geometry of X. And conversely, the gauge theory we get on X in 6 dimensions, that should depend on the topology of Y, but there's not so many 2-dimensional Calabi-Yaus. And in fact, the most interesting case, one which this is we expect Y to be our physical space, and so the most interesting case is when there's essentially no topology, just R4, in which case we should get the rank 1 Donaldson-Thomas theory on X. Rank being the Euler characteristic of Y. And it's a kind of 6-dimensional gauge theory, perhaps more familiar to mathematicians than to physicists. But it exists, it's well defined. And so now we would like to, in going from 4 to 4 plus 1 dimension, now we would like going from 6 to 6 plus 1 dimension, we would like to define some kind of partition function like this. Just like, so this would be this, so if this were in 4 plus 1 dimension, the partition function of a gauge theory on the manifold would reduce to some computation to the homology of some vector bundles on the moduli space of instantons in 4 dimensions. And by morally, this is in some sense morally it's just the same thing, but the problem to actually carry it out technically is the problem that the moduli space, the Donaldson-Thomas moduli spaces, the 6-dimensional instantons, are way too singular. And then they're just not the kind of spaces you want to ever examine by, so to speak, it's like one of some kind of chemical substance you never want to see. Because you ask the most naive question, like if I just in flat R6 or C3, I look at just points, a point-like instanton, and nobody knows what dimension of that space is. Some huge dimensional space with some kind of unspecified number of components, extremely singular. Anyway. So, but they do have a certain some redeeming features, and the features we're going to use.
What would be this? This is the
What's a perturbative? What's this?
What?
What is the perturbative part? What's over? I mean, the integrals over the instantons, I understand. But in 4 dimensions, you have also perturbative part.
The perturbative part has to do with like a regularized Euler class of. So what do you do? You're taking like a perturbative part in 4 dimensions. You take all sections H naught of just polynomials O of C2, and you have to take the Euler class of that, and you have to regularize this.
But I know where it comes from. In 6 dimensions, where it comes from.
In 6 dimensions, you have the same kind of thing. It's just the same thing. Replace C2 by C3 will be an infinite problem. It'll be some, instead of some kind of double gamma function, it'll be some kind of triple gamma function. It's not so interesting. Okay. So point is that to actually mimic what's done in 4+1 dimension, we're not going to do it, but we'll use some other features of this instanton moduli space. And the features we're going to use have to do with this instanton moduli space having a virtual class. I'll explain in a second what this means. So on very general grounds, and I'm not giving the subject any. So I mean, this is a very long subject, and I'm just gonna gloss over all credits and all details, and just give you the final result. So on very general ground, this instanton moduli, however singular, they locally near each point is going to look like a critical locus of a holomorphic function. Means our moduli space is embedded in some ambient smooth variety X as the 0 locus of a differential of a function. You have a differential of a holomorphic function that is a map from X to the cotangent bundle of X. It means section of this bundle rather, and then as the 0, it's where it's vanishing, defines M. Okay. So, however singular it's going to be, there is near each point there is there's an embedding of that in some smooth variety, such that the instanton moduli cut out as a critical locus of some function. And this gives M what's called virtual structures. Namely, what is it? What's the virtual? Well, for example, what's the virtual tangent bundle? The virtual tangent bundle is, well, if you had a smooth variety, then the tangent direction, smooth variety defined by some equation, that its tangent directions are the direction that correspond to variables, and you have to subtract the direction corresponding to equations. So now the variables, the deformations, well, if it sits inside some ambient X as a critical locus of a function, then the variables correspond to the tangent bundle of X restricted to M. And the equations is where the equation, after all, the equation for my moduli space are W prime equals 0. It's a section of this bundle. Therefore, the equations take value in the cotangent bundle of X restricted to M. That's a perfectly well-defined element it's a perfectly well-defined difference of 2 vector bundles on M. And it's called the virtual tangent bundle. It's virtual because it's the difference of 2 things. Virtual vector space is the difference of 2 vector space. Virtual bundle is a difference of 2 bundles. And once you have this, you can define like a virtual, the virtual canonical. Well, you take just the determinant of the dual of this. Makes sense? You can define the virtual fundamental class. The virtual O is the pullback of the 0 section in the cotangent bundle. This is extremely well-studied subject in math. I'm just going to gloss over this. And the key feature of this is they are self-dual. You see, if I take, this is a difference of 2 bundles, but this is a bundle minus the dual bundle. So if to say it here, that if I take the dual of the tangent bundle, or the virtual tangent bundle, I'm getting minus. Okay, that's the key feature. So the key feature of moduli of 6-dimensional instanton is that they have a virtual tangent bundle, which is self-dual. This is called self-dual, even though there's a minus here. And so our main proposal is whenever it's the case, whenever your supersymmetric states form moduli like this, we're also going to define the index by the following formula. It's sort of, you take this virtual half forms, the square root of the virtual canonical bundle, virtual half forms, tensor with the virtual O, and take the ordinary Euler characteristic of that. Right? Because in 6 dimensions, there's self-dual in 6 dimensions. It's just smooth in 4 dimensions. In six dimensions, it's so 6. Yeah, they somehow even in odd dimensions even in odd complex dimensions they alternate. This canonically is a square. Because you're taking the determinants of 2 dual bundles and take the ratio of those, this is going to be canonical as square. In principle, you can have your fermions twisted, so you can multiply this by a flat bundle, but this canonical has a square. And so this applies very generally. And in particular, and even though this looks kind of complicated, this is in fact much easier than most other things you can associate to a singular variety. You can if you have a very singular variety, you can associate all sorts of invariants to that, and people have. And well, I'm going to comment on that later in the talk a little bit. But that's in fact way simpler than other invariants you can associate to singularity. And what people certainly considered is just this. Like if you define K-theoretic Donaldson-Thomas invariants, that's just that same thing except the virtual half forms. So in our sense, in this sense, our contribution is just saying put the virtual half forms there. So if you look at like Barron's paper, he certainly considers the virtual class, and but the half forms are. That's our addition.
Do you have some kind of 3 epsilons here?
Oh yeah, sure. And in fact, it's much better to think of this not a number. It's an Euler characteristic of some complex. So whatever symmetries you have in the theory, they're all going to act there. And it's going to be virtual. This is Euler characteristic means it's a alternating sum of vector spaces. And so this will be a virtual representation in the sense of formal linear combination of representations of whatever symmetries of the theory you're going to have. And in particular, in this refined situation that we discussed, the rotation parameters, the rotation that we introduce on 2 sides, they're going to act here naturally, and so this would be a representation of that isometry group, and so that will be automatically refined. Yeah.
As opposed to 4 dimensions, there will be no analog of Coulomb moduli, or there will be.
It's not one field.
Yeah.
It's one field, right?
You
one
want. Oh.
You can have it in higher rank, but in fact with factor. Yeah. And so this will be, so since this is now a representation of some group, we'll study it in that generality. So we'll talk about the equivariant virtual index. Means this object considered as a virtual representation of whatever group of symmetries you have. So the assumptions that will be the following. So we'll start with a compact variety with a virtual self-dual class, self-dual virtual class, and let some group act on it. And what does it mean that group acts on this variety? But what am I going to do to the duality? The duality, generally speaking, if a group action, then the duality may pick up a factor. 2 things which were means it's no longer T virtual is exactly the minus its dual, but it can pick up just a representation, just a character of this group. Right? Okay. Suppose. Think of action of non-zero complex numbers on Z multiplying defining representation complex numbers. You go to the dual representation, you have to multiply by Z inverse. Okay, the original spaces were isomorphic. The dual pick up a character. Okay, so example of this, you take. So what's an example of this? You take the DT instantons on the Calabi-Yau threefold. That has some kind of chamber structure. You have to pick for this to be actually compact. You have to pick a particular chamber, which is called the Panner-Ponder-Thomas theory. Otherwise, it's not compact. And then delta is just the weight of holomorphic threeform. You have a group acting on a Calabi-Yau threefold. It may or may not preserve the holomorphic threeform. So the action of it on the holomorphic threeform is some character of the group, and so this would be the character delta. Like for example, if I take GL3 acting on C3, then the threeform is dx1, dx2, dx3, and delta is the determinant. Okay. So then from this assumption, this virtual index is now a representation of group, and it has a very simple. There's a very simple rigidity. For those of you who know the old story about rigidity, says that this particular thing, somehow the classical story is that something is just a trivial representation of the group. But this case, it's not necessarily trivial, but it only involves one character, namely the square root of this determinant. So now, when I said the square root of the bundle itself is defined canonically, but not equivariantly. So when you take the square root of the equivariant bundle, you may have to extract the square root of the character, but that's all right.
But character need not be a square. So what does this mean?
Well, if you have to extract, you just go to double cover of your group. Yeah, right. In this case, the character is not a square. So that's proven exactly like the old rigidity is proven. And so the old rigidity would be example. Rigidity says that some cohomology of some vector bundles, if you have a group action, then in fact the action is trivial. Like for example, if you look at continuous group acting on variety, and you look at Dirac cohomology, that in principle the group could act there, but in fact it acts trivially because it's just Dirac cohomology is the same topological cohomology, and therefore. So the next step is what about localization? So the localization for this virtual index takes the following form. Suppose I pick a one-parameter subgroup, and the subgroup has to be in the kernel of this. As I say, it has to preserve for Calabi-Yau threefold. It has to preserve the holomorphic threeform. And then for every fixed point of that one-parameter subgroup, I'm going to associate a number. And namely, so I look at this fixed point, and it has some attracting direction, some repelling direction. And I associate the index, which is the number of attracting directions minus the number of repelling directions. So it's in this particular example, there was one attracting, one repelling. Index equals 1 minus 1 equals 0. Right, so you choose. So the data. So right now, if I have a one-parameter subgroup and I have a fixed point of that one-parameter subgroup, then I have an index. And so this index goes in the localization formula and says that if I have let fi be components of the fixed locus, may not be isolated, then the index corresponding to the whole variety. So first of all, if sigma was preserving the so sigma composition delta is 1. So it means to say the action of the sigma preserves the holomorphic threeform. Then the fixed law say also if sigma was preserving delta, then the fixed law say also have a self-dual virtual tangent space. And so this is defined for the fixed loci. And the index of the whole thing is the sum contribution of the fixed loci times this factor raised to the power of the index.
Formula?
Oh yeah, sure. This is but that's somehow. Well, we don't have a. There's no. What?
It should be equivalent to.
Yeah, somehow. You know. Yeah, somehow the point of this talk. I mean, I'll comment on the motivic stuff later. Somehow, the point of this talk is not to think about the motives. Yeah, but certainly it is the case that if you have a torus action, then of course the motive of the whole variety is going to be a motive of the fixed loci, and then some bunch of fine lines somehow, right? Because there'll be the BB decomposition and the vector bundles or affine bundles over fixed loci, so that's going to be right. And so in principle, I want to. You think it's kind of trivial, but we will come back to this point later. Is that in principle that's a new formula for each choice of sigma, because you can have many different subgroups. They'll have many different fixed loci, and so the index is going to be very different things. And so then in principle, it's a new formula for each one. And if you don't know that they compute the same thing, it's pretty hard to know that they actually that all this. The right-hand side of all these formulas are equal.
How can you define repelling and attracting subvarieties if it's not smooth?
Well, that's actually you can look at the repelling this index for the virtual tangent bundle and the index for the actual tangent bundle is the same, because sigma preserves again. Because of this, whatever cancels, the contribution actually cancels on both sides. Yeah. So you can compute this index for the virtual tangent bundle, or you can compute it for the actual tangent bundle. It'll be the same. Okay. And so the trivial example is if your M is a compact Kähler manifold, which is a critical point of the zero function on itself, then your virtual tangent bundle is the tangent bundle of manifold minus the. And if I take the group of automorphism, take G, whatever automorphisms I have, plus one more C star, which scales the cotangent direction, then this C star will be the only part which C star is the subgroup that scales the cotangent directions. And so that's the only part, like this C star is delta. Right? Delta is trivial on this side, and it's an identity on that. And so if you look at the virtual O, if you unravel the formulas, you see that the virtual index is just the Hodge index, just that. But one of the parameters is set to 1. So it's the sum of HPQ. It's either 1 of this minus 1 of the delta. And so then, of course, the localization formula I just described is the usual localization formula for Hodge number. Okay. So. Like for example, for CP1, there'll be one attracting fixed point, one repelling fixed point, and sure enough, the Hodge character is delta square plus delta minus for CP1. You're gonna get delta 1/2 plus delta minus 1/2, which is for one attracting, one repelling. And so now we're going to get to the part with the index vertex. So maybe I should give credit for the old. So this is roughly what we do these days. So
It's very important to put the dates.
what?
You have the dates there?
Yeah, right. That's if you look what?
Very important.
95? 95?
Yeah, right. This is right. That's part of the picture. Right. Look, we can discuss the picture after.
You modified the right.
Oh yeah, sure, of course, yeah. Oh, come on, you're awake. That's good. Right. You mean?
No, mathematician and physicist. Oh, this is supposed to be.
No.
You change it.
Yeah, look, we can, you can find the 10 differences later. So now suppose now I've, I put this kind of sponge-like thing. Of course, this has no relation to whatever the Calabi-Yau is, but I mean, just here's some kind of place taker for Calabi-Yau. But now suppose it's something very concrete, something toric, which is like, the total space of O of minus 1 plus O of minus 1 over P1. Now let's see what this whole theory is going to specialize in the case when X is toric. And so if a torus, if the Calabi-Yau is toric, then the torus acts on everything, on logs on all the PT, DT moduli spaces, and the fixed points of that are isolated and look for in the familiar DT chamber, they're going to look like this. So imagine a toric polytope of X, and there's a pile of boxes at every corner, and then there is along any compact edge you can have some kind of these piles of boxes can merge along a compact edge. So it can, these piles can extend along compact edges. That's a familiar picture. And the way that is counted in the way this is counted in this formula now, it's counted by some little q for the number of boxes, some other parameter which we call big Q, times the thickness of the. So this is a certain number of boxes here, certain number of boxes there, and then there's a certain thickness to this edge. Like in this picture, it's 2. So you put q to the number of boxes, some other parameter big Q to the number of edges, and then this new parameter, you can say it refinement parameter to the number of index. And
They are in delta.
no. Oh, yeah, the product is in delta. So here, delta is the determinant, which is epsilon 1, epsilon 2, epsilon 3. Oh, whatever, yeah. Q, whatever. Exponential of epsilon 1 plus epsilon 2, epsilon 3. Right? So it's only this. It's only refinement. Or they have one parameter, and there's one parameter it has. Everything else cancels out by this rigidity theorem. So yes, right, the rigidity theorem is going to say it's only a function of the sum of 3 epsilons. So now we have to say what's the index. And to say what's the index, we have to pick a one-parameter subgroup. And we have to pick a one-parameter subgroup in where? In the kernel of to pick a one-parameter subgroup inside of my Calabi-Yau torus, which is characterized by the sum of 3 epsilons equals 0. So in fact, I got great many choices for this one-parameter subgroup. I can pick a line in the plane, and each choice will give a new formula, and the formulas will be visibly. I mean, they compute the same thing, but will be visibly different. So what's when you think about, go back to this picture, we'll think about the geometry of this picture. This is actually, the projection is projected to the board. It's really projection. So this whole diagram takes place in the dual to my entire Lie algebra of my entire torus. And this projection to the two-dimensional subtorus, to the dual of the two-dimensional subtorus, which preserves my holomorphic 3-form. So this picture, literal two-dimensional thing, sits in the dual of the space in which I have to pick a direction. So that means to say in this space I have to pick a covector. For every choice of a covector here, I get a new formula for the index. And previously there were the people have defined a certain, in the context of studying refined invariance, people have defined certain ways of counting things with boxes. It's called, this is particularly, well, there's a large body of work on this, but I would like to particularly mention a paper by Iqbal Kozcaz and Vafa. They define something they call refined vertex. And this refined vertex formula had a certain limitation in that it first required the toric Calabi-Yau to be of a special kind, namely it had a sense in this diagram, toric polyhedron, when you project it to the plane, it becomes some diagram there, and it has to have a set of edges, set of parallel edges that cover all vertices. These edges are called preferred, and most toric varieties don't have preferred edges. So if you consider the local P2, well, there's no way. So, but there's a theorem that are, so I'm not going to bother you with the general, what this index is in general, but it is the case that if my covector vanishes on an edge, so I have in the plane of my picture, I have edges, and I have a covector. So if the covector is such that it vanishes on an edge, so it sort of goes like this, then it's a theorem that our index weight equals to Iqbal Kozcaz Vafa weight. So in particular, our formula is, you can say we prove it in the sense that we deduce it from general principles, and we can say we improve it in the way that we wrote down a more general formula that applies to all toric Calabi-Yau varieties, not just the ones which have a preferred direction. In particular, it's also manifestly invariant so somehow the invariance under the choice of the refined direction is manifest because they all compute the same thing. And so now there's a large, on this refined vertex, there's a large body of work. I'm not going to try to survey it all. But for example, it already follows then from what's been already done is that this equality of the partition function, the equality of the 6-dimensional partition function with 4-dimensional, or 6 plus 1 dimensional with 4 plus 1 dimensional, is already, it's an theorem in all cases when there is a preferred direction. And so that's it's obviously just the beginning for some other talk, and maybe I'll just briefly mention on the some open problems and some connections, and then first of all, it's well, I don't know. That was supposed to be 50 minutes or an hour talk? An hour. Okay. So first, it's well, this in no particular order. First, you associate it to moduli space M, a vector space Z of M. And the first obvious question is that in what sense it is like, for example, if in the case when M was a smooth variety with the sort of trivial abstraction theory, or trivial whatever, that example when you have the trivial superpotential, that's right. Then that's just assignment of M to M cohomology of M. Right? And that's certainly a very functorial thing to do. And so now one expects one certainly expects something like this, some sort of factoriality of this assignment. And in particular, we, somehow certainly investigations that go back years and years and years, and certainly, I don't know, to at least Gapa-Kumar and Vafa have thought, people before them have thought some kind of way to associate something like a homology to general moduli spaces, and then they were expecting some SL2 cross SL2 action there, and this is some kind of SL2 cross SL2 action. Here should be a package, a part of some general package. I'm not going to discuss it now. Most importantly, there's certainly a very alternative approach. I mean, so not very alternative. We'll say something. So there is a totally different school of thinking. Is that you should really associate some motivic invariance to the singularities, and that's been a very popular subject. A lot of people worked on that, And I think certain mathematical results, like comparing, in particular comparing with things with the refined vertex computation. There are certainly papers by all these people, and maybe others. And so somehow, I think well, if I may say a word or two in defense of the approach we took, is that it seems it has certain advantages because it has some kind of direct physical meaning. You don't have to. You just look at what the Lagrangian ought to look like and think what is it that your theory is supposed to compute, and you led to our definition with the parameters having a natural physical meaning. As opposed to I'll let others to argue for the physical meaning of Z taking the values in the ring of motives, and it's infinitely easier to compute. Like to the best of my knowledge, there is no localization computation for this motivic invariant, even in the case of C3. And whereas this just comes here the stuff comes for 3, and most importantly, it actually agrees. And so for this whole situation, when both in the situation when both motivic and this K-theoretic approach are applicable, they're equal. And that's something I've been working on with Davesh. As I said, there's the motivic thing is extremely profound and very powerful, and applies in situations, maybe in some situations, one can think of some situations when it would apply where our approach wouldn't. And but it's certainly on the overlap of the range of applicability of the two theories, they're equal. And which is not so surprising, because if you have something with a well, okay, so yeah, okay, well, it's exactly an hour, so.
Question?
If you introduce some curve in O minus 1 plus element, which is equivalent.
Which is what?
Equivalent to some subgroup.
Well, I don't know. I mean, we haven't. There's like infinitely many things to compute here. Anytime you have a self-dual virtual class, you just do this and you get some number, or you get something. And we just, this particular thing we didn't try. Maybe you should try.
Well, no, let's take that.